And our last speech will be delivered by CHENG ZHANG. She is the principal researcher from Microsoft.
So today I'm going to share with you about our research on efficient element-wise information acquisition. I'm from Microsoft Research. I'm a principal researcher there, and I lead this project. Okay, of course, every project have a lot of collaborators, so I just want to show all of them here. So the content I'm going to present today is the work that I did in collaboration with all these awesome collaborators, and you can find our project homepage in the link below. So if you want to know more information, you can check out our homepage. So let's start. So information is actually not free. When we talk about machine learning, we talk about data. But every single data is not free, information not free. So for example, if we think about blood pressure is a data, this is a piece of information, but it need actually like a medical doctor take the device, measure your blood pressure, and so does it goes to many other scenarios, like if you want to recruit a candidate, and then you need a recruiter to ask questions, carry out the interview to just understand whether this candidate qualifies or not. So information is costly, and this cost can be in terms of money, and it can even bring potential risk in some medical setting with this invasive test. And of course, it's also costly in terms of time in many situations. So let's say two solutions. One solution is on the left-hand side, another one is on the right. So as a human, let's say Bob sees Alice coughing, and Bob thinks, oh, poor you, like then Bob asks Alice to take the temperature, and then Alice takes the temperature, and with the high fever, Bob decides to take Alice to the hospital. That's one solution, and that's very typical situation in real life scenario. And the second solution is Alice needs to input everything. She have all the information about her age, her number of pets she have, and then the AI assistant may say, okay, you need to go to the hospital. So I obviously will prefer solution one than solution two, because the decision is made much more efficient. I think by solution two, if I'm really serious ill, like after I gather all this information, I don't have the energy to go to the hospital anymore. So in this project, we really want to create a machine learning solution that behave like Bob before. So we want an automated solution, making decision in a personalized way, and provide this experience flow by suggesting what's the best next step. Like best next step is taking the temperature for the previous scenario. And so this is similar, like if we have everything we can gather, and the task here is we want to come up with some diagnosis. What's the disease at the current time? So maybe our agent can ask, what's the temperature first? Because agents think the temperature is the most useful and the kind of easy to get information. And with fever, maybe we gotta ask whether the patient has a cough. And then, with every bit of information you get, you update your belief and your diagnosis, and you can conclude one you're already confident. So no one needs to measure everything to make any single information decision. Okay, so this type of scenario just show up again and again in all different situations, all different domains. Like healthcare is typical. We measure only the relevant information from the medical doctors. Typical survey, no one likes survey for really long. And what if we can have dynamic survey and everyone save a lot of time? Same for recommender system. Education, we want to do online personalized education for the maximum performance. The same applies like a fintech and all the different industries. So here is a question, final question we really want to answer from the talk. How can we use machine learning to reduce the information cost while retaining the decision-making quality? So I'll go a little bit technical and present one of our solution. So our solution is called EDDI. It stands for Efficient Dynamic Discovery of High-Value Information. And think about the example, what's happening in Bob's mind when Bob sees Alice coughing. So Bob probably have estimation of the situation, right? He don't know everything, but he seeing Alice coughing, he probably think Alice may have cold, and potentially maybe have fever, maybe not. That depends on how bad the situation. It's very unlikely Alice will have malaria or something, right? So Bob, just observing Alice, will have an estimation of the situation with his own experience. And then the second step is Bob will think, to best take care of Alice, what should I gather more information? Like, what do I need to know to make such decision? And then he chooses at that situation to take the temperature to check whether Alice has fever or not. So then if we want to make a machine learning agent behave like Bob, we want to do exactly these two steps as Bob. So the first, we're going to have a model that can estimate what's the missing information. So the things that you don't know based on whatever you already observed, and in a probabilistic way. So we correspondingly will propose a missing value prediction solution with deep generative model. And in our solution, we'll have the second step like Bob. So we'll do an active element-wise information acquisition. So in general, to figure out which piece of information we actually really need for making the decision at the current time. Just a little bit of background for the first step. We use a deep generative model. In particular, this model is based on a type of model, like based on variational autoencoders. So variational autoencoder combines the best part of deep learning and probabilistic modeling. So in general, it's still a probabilistic model for a model like this. So it assumes there is a latent space Z that generates your observation. For example, the health status of Alice generates all different observations, like the body temperature, coughing, and all the symptoms. And it utilizes the deep learning procedure for an inference network called Q. And the whole optimization actually follows the standard probabilistic modeling optimization. It optimizes, the objective is called evidence lower bound. This is from traditional probabilistic modeling literature that is very standard to how to infer a model. And then in this way, because we combine deep learning and probabilistic modeling, so our model, the Z2X, is a deep neural network, and how we want to do the inference is also deep neural network. It will look in something like in the bottom. So we'll have input something like an X, like here I use a duck as an example. Then we encode it, or we call it the inference network, to a latent code Z, and then we decode it to the original image. So that's how this variational autoencoder works. And then the challenge here is such a model cannot handle partial observation. In our situation, Alice is coughing, and in the hospital situation, patient A may have medical test A, C, D, E, and another patient may have medical test A and B, because a medical doctor prescribed two different medical tests, right? And similarly, if the duck is missing, how can we do it? So here, if we want to use such a model that's utilizing deep learning and probabilistic modeling, but to impute or to predict missing information. So what we need to do is we need to change a variational autoencoder to a corresponding part that we call it a partial VAE. That's the model we propose. So the aim is we can infer the missing value from any observed value. So I have shaded X just means the X is partially observed. So from a machine learning perspective, for a model from left to right, which the left model is existing, one of the state-of-the-art model in many applications, to the right, how to handle partial information. So the optimization bound and everything still holds. So none of these mathematical changes, but the challenge is how can we design a deep learning that can actually take partial inputs. And let's recall it. We have the data looks like this. We have patients 1, 2, 3. They all have different medical tests. And then our observation in this sense is actually sets, right? So it can have different sizes, and it don't need to have the same order. So what we utilize is recall like the neural network. We need to be able to take partial input. We treat it as this partial input as sets. And then we utilize some framework from actually computer vision called PointNet. This is a framework that we kind of just utilizing a symmetric operator so that we can take an arbitrary number of inputs and they are in the nature of sets. And this was used in computer vision, was modeling point cloud because there are sets of points. But in this case, we can like these sets in our situation can be coughing, or body temperature, these different measures. And finally, combine this together, then we can have a partial variation autoencoder look like this. So we can have the input and the partial DAC, and then we can predict the full DAC. And actually, this is a probability modeling. So for every pixel, we have uncertainty estimation. And now we have the first part model. We can condition on arbitrary information, and we can predict unknown. So what's the first application we can think about to use such a model? It's a recommender system. So a recommender system, you can look at it as the rows are different users and the column are different items. Of course, each user only shopped or rated some item. It's a small subset, and we want to predict whether the user will like all these new products or items they haven't rated before, right? And then we use our model for this application, comparing with many state-of-art, like many baseline, at least at that time, this is 2019, we did get state-of-art results in one of the movie recommendation data sets, so that using such mixed value imputation, we not only be able to enable our application I talked about before, but this also can be used for generic purpose, such as recommender system. And now with the first step down, we have created this yellow box so that looking at coughing, we can estimate with uncertain estimation with everything that we don't know, whether we have fever, malaria, and all these things. We finish the first part, and next is how can we decide which question to ask? What's the best next step to take? And so I'll talk with you about the active element-wise information acquisition. So in this situation, so our boss actually want to find out condition on coughing. We call it XO, is observed information. And for every question we can ask, for everything we haven't observed, which one is the most informative one for our decision? So we want to find the question I, let's say, that give us the maximum information. That's we call it R. We call it information reward. So how can we quantify information reward? So we propose such objective. So what does it mean some information is very valuable? It means, like you can see this xi, adding this xi, x5 is our target, and we already have xo. So it says if we add xi, it makes biggest difference. The difference is measured by Kubic-Leibler divergence. So it means the two distributions, the blue one and the red one, the only difference is condition on xi or not, means condition on if we ask this question or not, make the biggest difference. So this will tell us how informative is this question. Of course, none of this is known, and that's where the first part of the model comes into place, because we haven't, before we ask Alice for temperature, we don't know the temperature, but we need to estimate it. We need to compute the expectation if we know the temperature, and that's where the expectation comes from, and that's why we need the first model to measure all these terms. And even with model, unfortunately, this is also an objective that is not very easy to compute, and we further used efficient approximation to be able to approximate this objective. And in this way, we can behave like Bob. So let's I'll just show a very small demo with a very toyish example. And the task here is to predict the house price. Instead of predict what's the disease, let's predict what's a house price. And you have a list of questions you can ask. So our solution, and the demo will show I'll list our solution on the left-hand side, and the baseline will be on the right-hand side. And so, of course, it's a double. We pretend we know what's the ground truth, and this will be marked here. And then this will be the model prediction for the decision, to predict the house price here on the top bar. So this will be a full list of questions we can ask. So in this situation, you can ask, okay, whether there is a highway around and all these things. And in medical setting, it means whether we want to take a new medical test. And this bar shows, like all these bars shows the information reward I just talked about. So the largest number means our model thinks the more informative this question is, more informative to get such information. And now we show the demo here. So this is with our model running behind, and you can see our model is dragged to the left and the baseline is on the right-hand side. And now here is a target value. So this is a decision we want to make. So when the prediction and ground truth meet, that's the target. So we will just want to have as accurate prediction as possible. And you can see we start to ask questions. This means we ask the first question and we start to submit the answer from the first question. And after we submit one answer, you can see the prediction change a little bit. And also meanwhile, all the information gain change a little bit, because after you get more information, if all the question also tells some information about each other. So as far as you observe some information, the information kind of value of the other question that you haven't asked also potentially decrease. And now we already asked the second question. You can see the more question you ask, the more accurate we predict, because we know more about the situation. And the goal, of course, is we want to use as least question as possible and to get as accurate prediction as possible. And you can already see this is after 3 questions. And our model is already predicting very, very close to the ground truth value, while the baseline is still quite far away. So that means this tells us with the same amount of cost, we can make the decision in a much higher quality, or we can say another way around. If we want to make a decision in a certain quality, we can use as little information as possible. We provide this experience flow by ask personalize the next question, always find out what's the most valuable information to acquire, given what we already know, will lead to the most efficient decision making in the short time, reduce the cost. So this is just a toy example to just show with the public data set. This list of questions can be like quizzes for students, like from teacher to test the students, to give exam, to understand whether the student learn or not. In this situation, we actually collaborate with a British company called EDDI. It's an online education platform. So we already show with our technology, like the teacher can understand student level much more efficient, and we can have personalized quizzes for each student. And with the data, with the collaboration, actually we want to contribute more to the community. We actually co-launched a Neural education competition last year, and the data set is also open online. And our technology is also directly used by this online education company. And of course, education is one case. As I mentioned before, this question can be a list of any survey, and it can be a list of technical question from interview for recruiting, and it can be a list of medical tests for diagnosis. And just to show some results on some more like standard machine learning benchmarks to show the behavior. And here are different standard machine learning benchmarks. And here are the steps, means how many question we ask or how many information we observe. And here are the prediction targets. So for the x-axis, the higher means higher cost, and y-axis means the lower the better, means the lower is the better decision quality. And the green one is the baseline, and the purple and black line are the 2 variations of our method. You can see with given any cost, we make the decision with really high quality, so we can make really efficient decisions. And the same with another data set on predicting patient mortality with different measurements. And you can see with actually 3 measurements, we can predict as good as with all 17 measurements. So, of course, we were very happy with this method, and apart from the education scenario, we also used in many other real-world scenarios. But sometimes the reality is just not as expected. So what's the new challenge here is the table, like the feature and the customer can ask, it can become in any form. It can be like age, gender, county, etc. So what's the problem here? So the VAE and all this type of model, or you can see many deep learning literature, they're dealing with data that have similar statistical type. So you think about like images, every pixel, they are the same type. They're 0 to 1, I mean, depends on how you scale it, or they're like a recommender system. They're ratings, ordinal number, 1 star to 5 star. And they have similar marginal distribution because they have the same meaning. They're just colors or something like that. But in real world data, so many data, when we start to deal with, what it shows is first they have different statistical type. It means like, excuse me, it means one dimension can be continuous. For example, height or blood pressure. And another dimension can be categorical, for example, gender. And then even so that have different statistical type. And secondly, also have different marginal properties. Let's say like the gender and county, they're both categorical, right? But gender depends on the survey, but maybe it has 3, like male, female, other, or maybe like 5. These are very few categories. But for county, it can have thousands even for US only, right? So then they have very different behavior and statistic properties. And then this deep learning method, many of them really have a hard time to deal with it. And what happens if we just use a naive VAE to fit the data looks like this? So this is pair plot, so the diagonal means marginal distribution, and off diagonal other pairs. Like these are just a statistic from 3 variables. And if we use the VAE and generate the data, it will look like the right-hand side. So you can see those in the best scenario, they should look kind of visually very similar, but you can see it doesn't. It's just because you can see this behavior and statistical distribution for all different dimensions, they are very different. So we need to, I mean, we claim our method can work for this multiple situation and every situation. So we really need our method to work on such data as well. And so we propose a new solution called, it's just designed for VAE for this heterogeneous mixed type of data. So it's actually, the idea is very, very simple. So the problem is if it's continuous data, it's very easy, like before deep learning, a standard thing is to normalize the data and all these things. But how can you normalize data when they're from different statistical types? So what we propose actually just to use something like the Bayesian autoencoder to first standardize the data. So for each dimension, for each type of data, like every single one, we first encode it to a latent space. And then for this way, then we can map every single dimension to a continuous variable. And with the prior, we commonly this continuous variable should be Gaussian-like because we regulate it. Maybe it's not ideal Gaussian, but it will be much more homogeneous. So we can just use a Bayesian autoencoder or autoencoder to map the data to a more homogeneous distribution. And this can, of course, can be applied to any statistical type and also any statistical property. And then we also want to, because we want to learn the data pattern, of course, we cannot just put it all separate. So at the second stage, we kind of do the same thing as standard VAE. Instead of applying it on the original data space, we just apply the dependence network on the space that we already, encoded our data. We are homogeneous. So we can learn the relationship among different feature dimensions. And this is the final model. So you can see, comparing to the previous graph model, instead of 1 plate, we have 2 plates because we have the inner plate is per dimension. The outer plate is to learn the relationship, and the optimization procedure will follow like a standard VAE optimization. And of course, we can use it for missing data. So if you look at marginal VAE, because you're only looking at 1 dimension, it doesn't matter for the VAE training, right? But for the dependence network, we can use exactly the same technique as I presented before for the standard partial VAE to combine it with point net so that we can have the partial elbow. So then in this way, we can have the model be able to work with data with different statistical type, but be able to do imputation as well. And so this is a different, this is just a simple procedure. If we train such model, how can we sample this unobserved data. So the first step for the encoder, we have our observation. We encode it to a latent space for each of them, and they are become homogeneous data. And then we use dependence network, model the relationship. And this is the encoder's dependence network. And then we can, with observation, we can decode to the full dimension, includes unobserved dimension, and then we can decode to the representation layer first, and then we further decode to the original space. In this way, we can do the imputation as what I talked about before, but with these special statistic types. And you can see that with the new method, this is in the middle, we can, the same toy data as before, we can recover how the data looks like, much more accurate, even like each dimension behave very differently. That is a significant improvement than standard VAE-based model. And of course, then we evaluated with many different standard machine learning benchmarks, both on data generation, also on kind of missing data imputation, and we can show like we perform best among all of them. And then, of course, we go back to our original setting. We want to behave like Bob. We want to do element-wise information acquisition. And here are the steps. Here are the decision-making. And if the model is broken, the decision-making quality cannot be good, and our sequence selection is all not working anymore. But with the new model, this as a red line, you can see we are able to behave exactly like we expected. With very few steps, we have very high decision quality, while with standard VAE or different other baselines, as a model does not fit such heterogeneous data well, they don't behave as we want them to be. Okay, then lastly, of course, then now we solve the problem that more application can use our method. But then there are situations when the data are really scarce. What if we have very little training data? And so we further extended the model. So before, when we think about it, it's always for deep learning, it's a point estimate of a parameter. And in this way, what we extend is first we make, instead of thinking such parameter as point estimate, we actually want to treat as the stochastic variable. So why we want to do it? First, when we treat as the stochastic variable, we have uncertain estimation. It performs much better just in the standard setting with very few data. And secondly, if we have no data to start with, in the extreme situation, not only few data, we want to acquire some training data in the first place. And then with such stochastic variable, we can also measure the epistemic uncertainty of the model. We can measure whether the model learned anything or not, and we can actively select which training to take. So we can both train the model very efficient and deploy the model to make this efficient decision making. And with this, if there are people into variational inference, so we actually propose a new method that combines amortized inference for local variables and stochastic gradient Hamiltonian Monte Carlo for the theta, so that our method can be able to scale to very large data set and at the same time being very accurate on uncertain estimation for the parameters. And here, if we use this model to acquire training data, it will have a little bit different objective. And here, as an objective, if we want to use such model, including training data collection as well. And the setting is we want to reduce the epistemic uncertainties. So you can see in the imputation setting, what we actually want to reduce uncertainty is on the model parameter. And in the predicted setting, we want to reduce uncertainty both for the model parameter and also for the prediction quality. And we can show with different experiments. And with different, here is instead of testing different things you can acquire, here are the total training data set size. And these are measured by element. And here is the decision quality. You can see with the PVE, it's like this. And with just the model we before, you can see with little training data, the performance is significantly better than PVE. If with infinite training data, like with much more, the performance starts to converge. And if we also use the active learning, element-wise active learning objective, and you can see it's even better. And this is in test. This is another one, like a similar plot for prediction task. This is the same mortality prediction with method data. This means numbers like elements, and the same behavior you can show. And one more thing I can see there is a light blue curve. This is traditional active learning. They are not element based, but rather thinking like to acquire the whole image in this setting, like have the records for the whole patients. And you can see that it's not as efficient if we actually can treat it as element-wise, because the information for every single number is actually really costly. And here means accumulate the number of the feature we predict, we acquire. And here we just want to show that there are nonlinear behaviors. So this cannot be simple rule-based system. The machine learning system really adapts through the learning process, taking into account the prediction quality, uncertainty estimation, and with different stage of training, they actually acquire features in different amounts. Okay, so then in this case, our method, like really our final scope to create the Bob, really works with the goal we have with different type of data and with different amount of data. So that's a summary of the talk. So here is just a top tip of the iceberg of the work we do in our team. And we created the Bob. We have the goal to really make machine learning agent behave like Bob, to have personalized decision making, to make decision as efficient as possible, and which correspond to with as low cost as possible. And we are collaborating with many partners to have real world application impact. So we have continuous innovation and co-innovation. Innovation is we're also doing a lot of more research, not only considering, okay, what's the best and next information to acquire, we also do what's the best next action, etc. And I said co-innovation is we actually not only Microsoft, also we collaborate with other partners. We look at the problem together, and it's a collaboration-based innovation that we aim not only to have machine learning research impact, but also directly and really real-world driven impact directly. And so if you have any questions, I mean, of course, now I'm going to open the floor for questions, but if you have follow-up questions or if you want to know more, please contact me. My email is on the slides. Okay, thank you very much. And I guess I'll open the floor to the questions.
Well, the audience. Okay, good. So, as I said, thank you very much for the presentation, and we will follow up. But first of all, let me not forget, this is a little gift from the organizers. This is you. And this mug will be posted for you. So this is just a small souvenir from the conference that you can remember giving this presentation here. From where are you calling in, by the way?
I'm actually in Sweden. Luckily, I'm one of the lucky person. Like I fly to Sweden and had some holiday time, and now I'm just going to stay here for another week, and I'm flying back to UK afterwards.
Sounds really good. Sounds really good. Then the mug will go to Sweden, or the address you provide, of course. Thank you very much. Second question to the audience, please go to the poll and please rate the speech. So as always, we try to get feedback from the audience. We try to understand how much they liked the topic, the presentation and everything. So feedback will be provided. And you can also write feedback and questions in the chat. So I see that there is already one question. Is there any published guideline to try the EDDI by ourselves? That's a question from Eddie Wang.
So first, you can see I listed all the paper below. So these are published papers. And we have example code published to all these papers. So you can actually find on GitHub, or if you look at the paper, we have the link attached. And meanwhile, if you are a company, so if you're a researcher, you can just use all this sample code and try it out. And if you're a company and would like to collaborate and use our technology for any of your product, so please directly contact with me. So it's possible, but we need to talk.
Yes, Thank you very much for the answer. So I see no other question there, but I have a question myself. So you have talked about the data, the missing data, how expensive it is to gather that data, and therefore it is very important that we make algorithms that can work on missing partial data and etc. And then on one of your screens, you have shown that one of the algorithms actually, I have, when you had the steps, and each step represented the next and the next information piece or the next question. Usually it was like converging, or let's say it was like declining always, the figures. But there were some cases when, with another question, the cost raised, the curve raised, basically. Can you explain? Is it a statistical behavior? Is it due to that, or is there anything behind which we need to understand? So, is there a possibility that if I know more, I could make a better, worse decision actually?
Okay, so generically, I mean, just let's think about machine learning, just a human. So generically, if you want to make a decision, the more information becomes more informative, right? Then the calmer, the better decision quality it is. But at some point, when there's too much noise, you also get a little bit confused, right? So I think this is the same for machine learning. Of course, there are optimization and model fitting issues. So currently, the plot I'm showing, we didn't stop. We just say how many questions we asked. So it can be possible that there are some information, there is pure noise, a little bit overfitting, right? That can happen. Like if, I mean, in general, I don't see it happen, but maybe use the tail a little bit. So generically, you don't see that happening, but it's not like absolutely not happening. It can a little bit, right? It's possible. There's no necessarily guarantee because we cannot guarantee the model don't fit to any noisy information. Meanwhile, for the plot we're showing, we didn't have stop criteria, but it's really easy to implement stop criteria. Because you have uncertain estimation, you can say we stop when we're confident enough, so then you don't even ask all these noisy questions. Or you can say we stop when the rest of the information really don't have much, this information reward anymore, right? So then this behavior, this also helps to stop such behavior.
I see, thank you. And I very much agree with you. Actually, yesterday we had a lot of philosophical talk about the ethics of AI and about the how the society will respond and the technology, how the technology can be trusted, how AI can be trusted. So I foresee that probably today in the chat room where we will have the audience mingling with us and have a little free chat, Shen, you will also join us there, right?
Yeah, of course.
Yeah. Then probably we can talk a little bit about the data, because today we had a presentation from a physicist who is researching the universe and collecting the data from the universe. So there the data is not cheap to collect, I would say, with these big telescopes and everything. So I think maybe there is something about the data, and it's very interesting to hear that. Of course, maybe if I have the more information, maybe that can also overfit my model, in case by case it can happen. However, I have one more question. Did you investigate the misinformation or the wrong data, so that if something in the data, especially when it comes to the patient, when it comes to the equipment measuring the blood pressure, it could be that it's malfunctioning. Can we use these methods to filter those cases, or what is your opinion in this about this question?
Okay, I really like this question, and this is actually, I think, a deep field, and really people starting to speak up on this data curation, right? So sometimes you have this toolkit data, and that actually removing them helps your algorithm, right? So I think first, there are many folds to this question. First, I think generically in our sense, we use probabilistic model. We do have like epistemic on the algorithm uncertainty estimation. Some of the error is just measurement error that our model have a certain degree of tolerance. But then it's in other situation, they are also related to this, auto distribution detection problem, right, with calibrated uncertainty estimation. So this line of research really aligns with our research because it commonly it's especially aligned with Bayesian deep learning, etc. And then another fold is this more, as you said, it can be from attack or this wrong information just to come from either really some malicious person put it into to want your model to fail, It can also be by mistake. So for this, I think this also opens the big question regarding all this security and all these things. So we do collaborate because in Microsoft research, we're a big research lab. There are other teams doing kind of security and all this work. We do collaborate with them as well, and we did look a little into such problem. But I will not claim I'm the best expert, and we have colleagues who are really guru in this field.
I see. Thank you very much for your answer. We have one more question from the audience. Oh, actually, two more questions. Were you considering deriving some kind of rules to have a quick shot on the next piece of information to get based on the existing ones? I'm sorry, I have to read the whole, expand this. So, were you considering deriving some kind of rules to have a quick shot on the next piece of information to get based on the existing ones without individual evaluation of the given instance?
Wow, that's a great question. Do you want to collaborate? so the thing is, that's something we did indeed look into, because you can think about let's say traditionally how the problem is solved. I know some medical doctors in Sweden, they have such platform, they do questionnaire and they want to do diagnose. They paid, they had 5 years of research actually generate one of these rule-based decision tree. These are human experts. And of course, when you have a rule-based decision tree, that's very kind of quick on runtime, right? But that's not automated. So in our way, we're in some way automatically generate such a thing. But as you said, currently we don't visualize it. We need to compute it every step. So one way is actually we can distill such our decision-making path into a rule-based one or a policy that is more explicit. And in this way, we call it an amortized policy, right? Because when the model is trained, you can generate all possible paths and then you can kind of extract the rules. So then that is one way to accelerate the decision-making in test time. But meanwhile, I just want to re-say that our method is actually really fast because it's deep learning based and it's just a forward passes on evaluating. So we're kind of fast enough for real-world uses in education domain. What you said, what's the question about, that can be further improve the speed and also have the benefit to make it more interpretable. And that's something we do have research direction and thoughts about it, but I'll hide the details. But please wait for our next publication.
Okay, I think Attila, who asked the question, has also written in the chat that you asked if he wishes to collaborate, and he is just saying yes. With a smile. So very nice. There is yet another question from David. Did you experiment with sequence models to learn to choose an ordered list of questions instead of one question?
So you mean so each step instead of one question, but have a set of questions? So I mean, is that the question, or it's more a sequential model?
I try to, maybe I just read it out once again. Did you experiment with sequence models to learn to choose an ordered list of questions instead of one question?
Okay, I have different way to understand the question, and maybe I'll just answer the question with my different with my uncertain estimation of different choice, how I can understand it. So first, if you want to ask next best question, the next best may not be one. You can have a group. You can evaluate information reward for a group as well, because their application, like a survey, they want to show one page and another page instead of one by one. So that's the method is feasible. Secondly, second for the question, I can understand it is a sequential models instead of our model. I'll just say that there are, so for such application, you can also solve it with, like, for example, RL-based models. We do have a paper called UDEN, that is use an RL-based solution. So you are kind of just, it's a sequential model, you try different sequences and you have the reward in the end. So you can formulate the same application with as an RL problem. That is feasible. We have work, there are a couple of related work doing the same, but they are not very sample efficient. Because with such model, it's very, very sample efficient. With RL model, you need a lot of training samples. That's, I mean, it's a generic RL problem. That's an open research topic. And I think thirdly, I don't know whether you mean this myopic and non-myopic setting, because if we do the next best question, it's still myopic. It performed pretty good, but it's not like, the RL is non-myopic, this solution is myopic. For performance comparison, non-myopic can be in some situation better, but most situation in real world seems not make that much difference. But you can also make such experiment design-based method myopic, like non-myopic. So there are colleagues had some work on this, because we just need to kind of like have this Bayesian version of rolling out. So we also can do non-myopic solutions with the Bayesian experiment design. So that's my three guesses of what the question means, and hopefully one of that answers your real question.
Okay, and as I said, there's always a chance to come to the breakout room and further discuss. I see Attila has some suggestions on some further things to try, so maybe that is also something we can take it there. So thank you very much once again for your presentation.